The night sky holds a secret, not one written in stars, but in silence. A silence so loud, so dark, it consumes even time itself. That secret, black holes. And sometimes, these monstrous voids meet. When they do, they don't just collide. They rewrite the rules of reality. Can two black holes truly merge into one? If so, what happens when the darkest forces in the universe crash together? What echoes do they leave behind? And how close are we, truly, to understanding it? This is not just science. This is a story about gravity gone mad, space torn apart, and time screaming for structure. Welcome to Mind Scramble, where we sleepwalk through the universe's strangest truths. The birth of the infinite. They begin not with a bang, but with silence. A silence so absolute, it absorbs everything: sound, sight, even time. You see, the story of a black hole is not born from darkness. It is born from light that lived too fiercely. A star, burning in the final act of its cosmic life, has held itself against collapse for millions or billions of years. Its outward pressure, from the nuclear fire in its core, has balanced its own gravity. But eventually, even the mightiest stars run out of fuel. And in that final breath, that dying moment, everything reverses. Gravity, long held at bay, seizes control. The entire mass of a star, sometimes 20, 50, even 100 times more massive than our sun, begins to fall inward. Not just the outer shell, not just the core, all of it, imploding, folding space. Compressing not into a denser star, but into something else. Something no longer recognizable as matter. Something so dense that no structure can exist. No atoms, no neutrons, not even quarks. This is the singularity. It is not a point in space, but rather a failure of space itself. A moment where our equations scream, where math gives up and time ceases to function. It is not a thing. It is a catastrophe of physics. A place where the rules that govern all we know, energy, mass, distance, simply do not apply. And surrounding this singularity is an invisible sphere, the event horizon, the surface of no return. Anything photon, atom, ship, scream, that passes this boundary is forever lost to the universe. Not because it's destroyed, but because the very notion of distance becomes meaningless inside. To observers far away, the event horizon looks like a dark sphere. To the unlucky and falling object, time stretches, space warps. The universe itself turns into a tunnel that points inward. Every path curves toward the center. A black hole is not just a hole. It is not an object. It is the ultimate consequence of mass existing in a universe governed by Einstein's general relativity. The infinite curled into a point. The graveyard of information. The silence at the end of light. But here's the irony. Something so terrifying, so absolute, begins with a star, a light, a heat, a heartbeat in the dark. And in dying, it doesn't vanish. It inverts. It becomes the very undoing of the space around it. And this is where it all begins. If the singularity is the heart of the black hole, then the event horizon is its skin, but it's a skin with no substance, no texture, and no mercy. It's not a wall or a barrier. You won't feel it as you cross it. There's no shimmer, no warning, no sudden shift in air or pressure. You step through it the same way you might cross a shadow, but once you pass that invisible frontier, the universe no longer offers you any options. Every possible path leads inward, not because you're being sucked in like water down a drain, but because the very geometry of space changes. The direction of forward becomes a curve toward the singularity. A way no longer exists. Escape is no longer a valid command in the language of the cosmos. Let's make that clearer. Imagine you're an astronaut drifting toward a stellar mass black hole. Maybe you've been orbiting it for study, just outside its reach. At first, everything seems normal. Your ship stabilizes. Gravity feels intense but manageable. You look out the window, and space warps. The stars behind you begin to stretch into long arcs of blue. Ahead, nothing but blackness. Not darkness, blackness. A region of space where even starlight has stopped traveling. As you drift closer, time itself begins to behave strangely. Not for you, your heartbeat, your thoughts, your breath, all move forward at a normal pace. But to someone watching from far away, back at mission control, say your ship begins to slow down, slower, slower, still, until you seem frozen on the edge of the black sphere. You're not really frozen, of course. You're falling inward at ever-increasing speeds. But time near the event horizon has stretched so dramatically that from an outside perspective, you never quite cross it. You become a ghost, a fading image, a shadow of yourself, smeared on the edge of the abyss. But to you, it's different. You cross the event horizon without noticing. No alarms go off. No instruments flash red. No pressure builds. You simply continue, and the outside world slips from view. Stars vanish. Time loses meaning. You are alone, not just physically, but existentially. You are in a realm where reality has been rewritten, a place where causality, motion, and logic bow to the singularity's will. Let's take a step back. Why does the event horizon exist in the first place? It's a consequence of general relativity, Einstein's gift to the 20th century. In his theory, gravity isn't a force pulling objects together. It's the warping of space and time by mass. A planet curves space a little. A star curves it a lot. A black hole. It folds space so completely that the fabric closes in on itself. The event horizon is the limit where space folds inward so sharply that even light traveling at the ultimate speed limit can't find a way out. It's not just a speed trap. It's a topological prison. Here's another way to picture it. Imagine space as a flowing river. You're in a boat, paddling downstream. The closer you get to the waterfall, the event horizon, the faster the current flows. Far upstream, you can paddle against the current and stay in place. Closer, it takes more effort. Right at the edge, the current matches the speed of light. No matter how hard you paddle, even with rocket boosters, you can't fight it. Beyond the horizon, the current flows faster than light. There is no returning. And what lies past that edge? We don't know. Physicists can calculate the outside of a black hole with stunning accuracy. But beyond the event horizon, our math breaks. It gives us imaginary numbers, infinities, undefined quantities. The event horizon is not just a boundary of a black hole. It is the boundary of our understanding. Now, here's where things get strange. Some black holes might not even have event horizons. Theoretical objects called gravastars, or dark energy stars, have been proposed as alternatives, exotic constructs where matter is compressed incredibly, but doesn't collapse into a singularity. They might mimic black holes so closely that we wouldn't be able to tell the difference, until something crossed the boundary and came back out. So far though, all observational data favors the traditional view. Black holes have event horizons. Things go in, nothing comes out. But does that mean the information is truly lost forever? That question leads to the information paradox, which we'll explore soon. But for now, it's enough to know that crossing the event horizon isn't just about being swallowed. It's about being erased from the universe's memory. The laws of physics, as we know them, work wonderfully outside the horizon. But inside, they become rumors. We don't even know what time means in there. Some say time flows toward the singularity, the way space flows into the horizon. Others say time ceases entirely, or becomes imaginary, or loops. Inside the horizon, you're not just in a different place. You're in a different type of place. A region of spacetime where the directions are wrong. The distances don't make sense. And every possible trajectory ends in the same place. the singularity. Some physicists have even proposed that the event horizon might be a kind of holographic screen, a surface on which all the information of what's fallen in is somehow encoded. Not destroyed, not gone, but scrambled into a pattern we can't decode. This is the idea behind the holographic principle, and it might be the only way to reconcile the eternal pull of gravity with the delicate bookkeeping of quantum mechanics. But that's for another subtopic. For now, let's linger here, at the very edge. The event horizon is not a location you can visit, photograph, or land on. It's a threshold, and thresholds are always about transformation. The moment you cross, you are no longer part of this universe. You exist inside it, yes, but you are no longer in touch with it. Your messages can't get out. Your energy can't get out your screams. Lost, and yet, we can hear the black holes speak, not with sound, not with light, but with gravity. Because when two of these monsters dance, spiral, and merge, it's the horizon itself that ripples. It's the event horizon that collides, stretches, and rings like a drum across the fabric of space. But to understand that, we first need to understand the singularity at its center, and that is what we'll dive into next. There are places in the universe where the laws of physics guide, predict, and explain every observable thing. The spin of planets, the life cycles of stars, the orbits of galaxies, everything, from the flicker of a candle to the explosion of a supernova, can be understood, mathematically, logically, predictably. But then, there's the singularity. This is where that order dies. When we speak of a black hole, we often describe the event horizon, the outer boundary, the invisible sphere around the abyss. But that's not the black hole itself. That's just the edge of its influence. Inside, at the center, is something even stranger. Something that defies not only observation, but imagination. A place, or rather, a point where all the mass of the collapsed star has been compressed into zero volume. Infinite density. Read that again. Infinite density. This isn't a metaphor. It isn't hyperbole. It's the literal result of Einstein's field equations when taken to their extreme. All the mass, all the gravity, all the curvature of spacetime. Everything collapses into a single, infinitely small point. A dot, not just without dimensions, but without definition. This is the singularity. And here's where it gets deeply uncomfortable. Because we don't know what this means. We have no equation for it, no image, no working model. In physics, when a quantity becomes infinite, it's usually a red flag, a warning that the theory being used has reached the end of its validity. It's like a calculator flashing error because you've divided by zero. Mathematically, you've broken something, and that's exactly what happens here. Einstein's general relativity predicts that if enough mass collapses into a small enough space, the geometry of spacetime will curve infinitely. But quantum mechanics, the other great pillar of physics, refuses to make peace with that idea. It says that matter and energy operate in discrete units. Nothing is truly infinite. Everything has uncertainty. Nothing can be both perfectly located and perfectly energetic. So, when we apply both theories at once, they scream at each other. Relativity says, the singularity exists. Quantum theory says, that's impossible. And thus, the singularity becomes a wound in our understanding. A blank space on the cosmic map, labeled not with "here be dragons," but something worse. Here be equations that lie. But, let's explore what we think might happen in this unknown. If you were falling into a black hole, and somehow survived the tidal forces near the event horizon, perhaps falling into a supermassive black hole where those forces are gentle until much later, you'd be pulled ever inward. As you approached the center, gravity would become overwhelming, not just stronger than any planet or star, but infinitely strong. The curvature of space-time would stretch and twist around you like a cosmic whirlpool. Directions lose meaning. Space begins to contract in all dimensions. Time, as measured by your own experience, continues, but the outside universe has already lost track of you, and then, there's no then. The singularity is not just a point in space, a temporal dead end, a place where all trajectories, all paths, all world lines end. If the universe is a book, the singularity is where the pages tear and collapse into a knot. You're no longer inside the story. Now, let's ask a daring question. Is the singularity real? Or is it just a mirage and artifact of our incomplete understanding? There are several theories about what the singularity might actually be. Quantum gravity resolution. If we ever develop a successful theory of quantum gravity, a merger between general relativity and quantum mechanics, it may smooth out the singularity. Just as atoms prevent a star from collapsing forever, perhaps quantum geometry prevents spacetime from truly hitting infinite curvature. Instead of a singularity, the center of a black hole may be a dense but finite core, a kind of Planck scale fuzzball, governed by unknown rules. Loop quantum gravity. In loop quantum gravity, spacetime is made of discrete loops, like a woven fabric. Under this theory, the core of a black hole might bounce, transforming into a white hole, an object that spews out matter rather than swallowing it. This could mean black holes are not endpoints, but transitions, bridges between cosmic phases. String theory. In Fuzzballson string theory, particles are one-dimensional strings, vibrating in higher dimensions. Some variants suggest that the singularity is replaced by a tangled mass of strings, a fuzzball, with no sharp boundary, no point of infinite density, and possibly even structure on the quantum scale. In this view, the singularity is a myth, and the interior of the black hole is complex, chaotic, and still very much part of the universe. The holographic principle. Here's where things get even weirder. Some physicists believe that everything inside a black hole, including the singularity, is encoded on the event horizon itself, much like a hologram. From this perspective, the singularity is a mathematical illusion, a projection from a surface, with no interior. This is the holographic principle, and if it's true, the entire universe might be a projection from a distant cosmic boundary. But until we have definitive proof, we are left with one unavoidable truth: the singularity marks the failure of our current physics. It's not just a mystery, it's a challenge, a hole in the tapestry of knowledge, a place where new laws must be born. Because if we can't describe what happens at the singularity, we can't fully explain black holes. And if we can't explain black holes, we can't explain the universe. Because black holes aren't rare. They're not exotic outliers. They are fundamental. They sculpt galaxies. They distort time. They shape the distribution of matter on cosmic scales. And when they merge, when two singularities collide, the universe doesn't just tremble. It listens. The gravitational waves that result from such a merger are not merely noise. They are the roar of singularities combining. They tell us, with ripples in spacetime, that something unimaginable just occurred. So what happens when two singularities merge? Do they become a bigger singularity? Or is something lost? Is something hidden? Or could a merger of singularities unlock something we've never seen before, a breach in the boundary of existence? To answer that, we must continue to spiral deeper into the structure of the black hole. Next, we must talk about how black holes spin, because it turns out, they don't just sit there passively, they twist the universe around them. Spin and charge. Black holes with personality. Black holes are often portrayed as featureless monsters, simple spheres of darkness, devouring everything in their path. But that's far from the truth. In fact, black holes have character, not personality in the human sense, but traits, qualities, identifiers. Under general relativity, a black hole can be completely described by just three physical properties: mass, spin, angular momentum, charge, electric charge. Together, these make up what physicists call the no-hair theorem, the idea that black holes have no hair. No distinguishing features beyond these three measurable values. Number: bumps, no wrinkles, no history of what they once were. Collapse anything, an elephant, a planet, a star, and once it becomes a black hole, all that messy detail disappears. Only mass, spin, and charge remain. But within those three traits lies an entire universe of complexity. Let's begin with spin. The spinning abyss. Almost nothing in the universe stands still. Planets rotate, stars spin, galaxies swirl. And when something collapses into a black hole, its rotation doesn't vanish, it intensifies. This is conservation of angular momentum, one of the most deeply rooted laws in physics. When a star collapses into a black hole, the mass moves inward, but angular momentum must remain. So what happens? The black hole spins, and the smaller it gets, the faster it spins. Some black holes are predicted to rotate near the speed of light. This isn't just a wild concept, it's been observed. Astronomers measuring the X-ray emissions from matter swirling around black holes have detected the signatures of extreme spin beyond anything we can imagine on Earth. But here's the twist. A spinning black hole doesn't just rotate, it drags spacetime around it. This phenomenon is known as frame dragging. Imagine spacetime as a thick molasses. Now picture a sphere spinning within it. The molasses doesn't stay still. It's pulled, twisted, warped around the object. That's what a rotating black hole does, not just to space, but to time itself. This creates a region around the black hole called the ergosphere, a warped, swirling zone outside the event horizon where nothing can remain stationary. Even light, even time, gets pulled into the vortex. If you enter the ergosphere, you can still escape, but only if you ride the spin. If you try to resist, it's like swimming against a cosmic current, stronger than anything you've ever felt. Now let's add the second trait, charge. Asterisk, electrifying the void. A black hole can also carry an electric charge, though in practice, most astrophysical black holes are thought to be neutral, because charged particles tend to attract oppositely charged particles, neutralizing the system over time. But in theory, a black hole can carry positive or negative charge. A charged black hole behaves differently. Its gravitational pull is modified by electromagnetic repulsion. For instance, a positively charged black hole will repel other positively charged particles. The more charge it has, the more this repulsion counters gravity. But too much charge and something fascinating happens. The equations describing black holes, specifically the Reisner-Nordström metric for charged black holes, tell us that if the charge is too great, it prevents the formation of an event horizon. The singularity becomes naked, exposed to the outside universe. This is more than just theoretical embarrassment. It violates what physicists call the cosmic censorship conjecture, the idea that singularities should always be hidden behind an event horizon. If one were naked, it could expose the raw laws of the universe, unshielded, chaotic, and possibly paradoxical. But there's something even more bizarre. Asterisk, the Kerneman black hole. Alan 1. Monster combines spin and charge in. You get the most general form of a black hole, the Kern-Newman black hole. This entity spins, it charges, and it bends the fabric of reality in ways that border on science fiction. It has a ring-shaped singularity. It can have multiple event horizons. And it can, under the right conditions, contain closed, time-like curves paths through space-time that theoretically allow a traveler to return to their own past. Yes, you read that correctly. If nature permits a sufficiently exotic Kern-Newman black hole to form, and if you could survive the extreme gravitational forces, it might be possible to trace a path through its interior and come out before you entered. This is where black holes go, from astrophysical phenomena to cosmic puzzles. They are no longer just collapsed stars. They are gateways, possibly even bridges, between different regions of the universe or different timelines altogether. And all of this complexity arises simply because the black hole has spin and charge. Mass pulls you in. Spin twists, space-time. Charge repels or attracts particles. Together, they shape the black hole's identity, a character, a fingerprint in the void. Why it matters? Why should we care whether a black hole spins or holds charge? Because these traits aren't cosmetic, they change everything. A spinning black hole can store energy in its rotation. Under the right conditions, this energy can be extracted via a process known as the Penrose process. This theoretical technique involves entering the ergosphere, splitting a particle into two, and having one fall into the black hole, while the other escapes with more energy than it came in with. It's like stealing energy from a whirlpool by throwing something into its current. Charged black holes, on the other hand, could influence the behavior of matter and fields around them. They change the dynamics of Hawking radiation, the stability of the event horizon, and even the way information behaves. And when two black holes merge, their spins and charges determine the nature of the final object. The gravitational waves we detect from these collisions carry the imprint of these values. From billions of light-years away, we can detect the spin signature of a black hole that no longer exists, just its echo in the fabric of spacetime. These waves are like fingerprints in the void. They whisper, this black hole was spinning. This one wasn't. This one carried charge. This one danced like a storm before it died. And that brings us to the question you came here to ask. When two black holes, each with their own mass, spin, and charge, collide, what is the result? Is the outcome just a bigger black hole? Or does something stranger happen? Could the merging of two complex singularities, each spinning, each twisted form, something that isn't just a continuation, but a mutation, a transformation? We've seen the echoes, we've measured the waves, but the core, the final moment of impact, is still hidden. And to understand that, we must now turn to the phenomenon that revealed it to us for the first time. Spaghettification. Death by gravity. It sounds like something out of a cartoon. Spaghettification, as if a black hole is an interstellar pasta machine. But don't let the absurdity of the word fool you. It describes one of the most gruesome, fascinating, and inescapable phenomena in the known universe. Imagine falling feet first into a black hole. You're not just plummeting, you're being unraveled, stretched, dismembered at the atomic level. Why? Because gravity is not uniform. It changes with distance. The closer you are to a gravitational source, the stronger its pull. In everyday life, we barely notice this. The difference in gravity between your head and your toes on Earth is negligible. But near a black hole, this difference becomes monstrous. As you descend, the pull on your feet becomes exponentially stronger than the pull on your head. It's not just a difference, it's a chasm. The tidal forces, the difference in gravitational acceleration, are so severe that your body would begin to stretch. Ligaments tear, bones separate, molecules distort. Eventually, you're reduced to a single line of atoms, all falling toward the singularity. This isn't science fiction. It's physics. The deeper into the gravitational well you fall, the more intense the stretching becomes. The process happens quickly, horrifyingly so. There's no real time to scream, though even if you did, the sound wouldn't escape. And just before your shredded body reaches the singularity, something else happens. Time, from the perspective of an outside observer, grinds to a halt. To those watching from afar, you freeze on the edge of the event horizon. Your final expression, stretched across eternity. But from your own perspective, you fall normally, until everything compresses into one final point. The mathematics behind this are not abstract. They're calculable, testable, and verified by countless simulations and equations. The name may be whimsical, but the process is brutal. And it happens, not just to people, but to stars, gas clouds, even light itself. This is why the event horizon is so feared. It is not just a boundary, it is a threshold to torture, to an irreversible transformation. Once you cross it, the very geometry of space betrays you. The notion of down becomes in, and in becomes forever. Yet, strangely, the process depends on the size of the black hole. In a stellar mass black hole, say, 10 times the mass of our Sun, spaghettification occurs before you cross the event horizon. The tidal forces are so intense, they destroy you in the approach. But in a supermassive black hole, like those at the centers of galaxies, the tidal gradient is gentler. You might cross the horizon unscathed, only to be shredded much later. Inside, in either case, you die. But how you die depends on what's doing the killing. This reality, where a falling astronaut becomes a ribbon of atoms, is not poetry. It is what happens when Einstein's equations rule the cosmos with no mercy. Spaghettification is not death by crushing, it's death by separation. You are pulled apart, not by force, but by the difference in force. It is death by differential. A lesson from the black hole. It is not the fall that kills you. It's the stretching, and once you are reduced to your most elemental form, there is no body, no identity, no memory, only motion. Motion toward a place where even the concept of place no longer exists. The spaghettification of matter is the black hole's signature, and every falling object, no matter how vast or small, becomes part of its story, a thread added to an endless cosmic pasta that no one will ever taste, touch, or see again. Information loss paradox. Do black holes delete? Imagine this. You're standing near a black hole, and you toss in a notebook. It's filled with scribbled secrets, formulas, thoughts, everything about your identity. Page by page, it falls inward. First, it glides through space, then begins to accelerate, warping, under gravity's pull. Eventually it crosses the event horizon and vanishes. Gone, irretrievable, a puff of nothing. No light comes out, no echoes. The notebook is simply erased from the universe. But now imagine this, that notebook wasn't just paper and ink. It held information, the arrangement of atoms, the sequence of thoughts, a pattern that was unique. Quantum mechanics, the bedrock of modern physics, has a strict rule. Information cannot be destroyed, not erased, not hidden, not even scrambled beyond recognition. The total information in a closed system must be preserved. So, what just happened? This is the information loss paradox, one of the most profound unsolved problems in theoretical physics. And black holes are at the center of its island, devouring, and seemingly lawless. The heart of the paradox arises from the collision of two perfect theories. General relativity, which describes gravity and the behavior of black holes with staggering precision. Quantum mechanics, which governs particles, energy, and information on the smallest scales. Each theory works flawlessly on its own. But when we try to apply both at once to something like a black hole, we hit a contradiction. General relativity says, once something passes the event horizon, it's lost forever. The black hole gains mass, maybe spin or charge, but nothing else matters. The original form of what fell in its structure, its data is erased. Quantum mechanics says, that's impossible. If you destroy information, you violate unitarity, a fundamental principle that keeps the universe logically consistent. So which is it? Does information really vanish into the singularity? Or does the universe preserve a record, hidden in some form we haven't yet understood? A historical twist. Hawking radiation in 1974. Stephen Hawking flipped the physics world upside down. He proposed that black holes aren't completely black. Thanks to quantum effects near the event horizon, virtual particle pairs pop into existence, one falling in, one escaping. The result: the black hole emits radiation. Hawking radiation. It's real, it's weak, but it exists. And here's the terrifying implication. As the black hole emits radiation, it loses mass. Slowly, agonizingly, over trillions of years, it shrinks, until eventually, it evaporates, completely. So the question becomes, what happens to the information that fell in? If the black hole vanishes, and all it leaves behind is Hawking radiation, a thermal, random emission, with no memory of the past, then the information is gone. That would mean quantum mechanics is wrong, that the universe allows irreversible deletion of data, and that idea, it breaks everything. It would imply that the universe is not deterministic, that you could rewind the clock and never recover what was lost, that entropy doesn't just increase, it obliterates, and in a world governed by logic, that's unacceptable. Proposed solutions. Physicists have offered many bold and often bizarre ideas to resolve this paradox. Let's explore the leading ones. Asterisk information is hidden in the Hawking radiation. This idea suggests that Hawking radiation isn't purely random. It might appear thermal, but deep within it lies a subtle correlation, tiny imprints of the information that fell in. Over time, as the black hole evaporates, it slowly releases that information back to the universe. But proving this is difficult. It would require decoding entangled quantum bits spread across vast radiation fields. Like unmixing a drop of ink from the ocean. Technically possible, practically impossible. Still, this is the most favored resolution today, especially after developments from the ADS-CFT correspondence in string theory, which suggest that information must be preserved. Asterisk information is stored on the event horizon. This leads to the holographic principle, one of the most mind-bending ideas in modern physics. It proposes that all the information about the 3D interior of a black hole is actually encoded on its 2D surface, the event horizon, like a cosmic hard drive. This would mean the black hole's surface area holds all the data of what has fallen in, and as it evaporates, that information can be released bit by bit through Hawking radiation. It turns our understanding of reality inside out. It suggests that the entire universe might be a hologram, our 3D experience, a projection from a 2D boundary beyond our perception. Asterisk remnants remain. Some theories suggest that after evaporation, a tiny remnant remains, a Planck-sized nugget containing all the lost information. These black hole remnants would be nearly invisible, incredibly dense, and litter the universe like forgotten seeds. But this creates its own problems, mainly that it would lead to an infinite number of remnants over time, threatening the stability of physics itself. Asterisk information escapes through wormholes, another radical idea. The information doesn't stay in the black hole or escape as radiation. It slips out through quantum wormholes that connect black holes to other parts of the universe. This isn't just fantasy. Recent papers in quantum gravity propose that E equals EPR, deep connection between entanglement and wormholes. Could this mean every black hole is connected to another region of space? That the things we lose aren't lost, just relocated? Asterisk there is no paradox because the black hole interior doesn't exist. The most extreme view. Maybe we've misunderstood black holes entirely. The event horizon may not lead to a true interior. Some suggest the horizon is a firewall, a wall of quantum energy that destroys everything instantly. Others propose it's a fuzzball, a tangled mess of strings, where nothing actually falls in. In this view, there's no singularity, no interior, just a surface of quantum chaos. But these theories, while fascinating, are still theoretical and controversial. Asterisk what the universe is trying to tell us. What's at stake here isn't just black holes, it's reality itself. If information can be lost, then the universe doesn't play fair. The laws of physics would allow for irreversible erasure, like deleting a person from existence with no trace. It would also open the door to paradoxes. Imagine building a quantum computer, feeding it into a black hole, and evaporating the whole. The output thermal radiation tells you nothing. The computer's thoughts, calculations, memories, gone. Logic collapses. That's why physicists must find a solution, and they're getting closer. Thanks to gravitational wave astronomy, quantum information theory, and advances in string theory, we may one day crack this mystery. For now, we're left with echoes. Black holes hum across the universe with a frequency we're just beginning to understand. Each wave carries a fingerprint of what was lost, and perhaps, encoded in those oscillations, is the answer. Because a universe that forgets is a universe we cannot trust. Asterisk the information loss paradox. Do black holes delete reality? It's a simple question, but it shattered the world of physics. When something falls into a black hole, is the information it contains lost forever? In other words, if you toss a book into a fire, you destroy the pages, sure, but in theory, if you collected the smoke, the ashes, the emitted light and heat, you could reconstruct everything that was written. Nothing is truly lost, just transformed. But if you throw that same book into a black hole, now we face a dilemma. Because according to general relativity, the black hole absorbs the book and forgets it. All we get in return is more mass, a stronger gravitational field, and eventually, in Hawking's prediction, radiation that's completely random. No trace of the book's words, ink, language, or structure. It's gone. This leads us to the information loss paradox. One of the most controversial and mind-bending problems in theoretical physics. Let's break it down. The black hole side. Erasure. Einstein's general relativity treats the black hole as a one-way system. Once something falls past the event horizon, it contributes to the black hole's mass, spin, and charge, and nothing else. This is why black holes are said to have no hair, no identifying features, no memory of what formed them. Two black holes of the same mass, spin, and charge are indistinguishable, even if one was made of dark matter and the other of kittens. But here's the catch. Quantum mechanics says that information can't be destroyed, ever. The wave function of a system must evolve unitarily, meaning every quantum state must be reversible in principle. The universe keeps the receipts. So, what happens when quantum law meets gravitational authority? Hawking radiation complicates things. Stephen Hawking changed everything in the 1970s when he showed that black holes aren't eternal. Due to quantum effects near the event horizon, they emit faint radiation, now known as Hawking radiation, and over time, they evaporate. Here's the problem. Hawking radiation is thermal. It carries no information about what fell into the black hole. So when the black hole finally evaporates completely, all the information, books, stars, civilizations, is gone, which violates quantum mechanics. This conflict between the smooth geometry of relativity and the strict rules of quantum theory is the beating heart of the information paradox, and the stakes are enormous. If black holes can delete information, then our entire understanding of cause and effect, of memory, of predictability, is in question. If they don't, then we must radically change how we think about black holes, or quantum theory, or both. Proposed solutions, and why they're all weird. Physicists have proposed dozens of ideas. Some say the information escapes in Hawking radiation, but in a highly scrambled form, like a puzzle, whose pieces are scattered across the universe. Others believe the information is encoded on the event horizon itself, in a 2D surface that acts like a cosmic hard drive. This idea gave birth to the holographic principle, suggesting that our 3D universe might be a projection of 2D data. But more on that later. Some theories suggest information gets funneled through wormholes into baby universes. Others claim it's stored inside a firewall, a violent surface at the horizon that annihilates anything falling in, preserving information in a quantum blaze. Even more radical proposals say black holes don't destroy information because they don't exist in the way we think they do. They're quantum objects, entangled, fuzzy, and not truly separate from the rest of the universe. And then there's the final horror. What if black holes really do destroy information? That would mean quantum mechanics is incomplete, that determinism is dead, and the universe itself has loopholes where reality can be overwritten, that what's true today might be unrecoverable tomorrow. Imagine a hard drive that, once deleted, not only loses files, it loses the concept of ever having had them. Why it matters to you? This isn't just academic debate. If information can be lost, then memories, identities, and laws of physics themselves are negotiable. You could be living in a part of the universe where something else once was, and no trace remains. Not even a shadow. You might ask, why should I care? Black holes are far away. But this paradox reaches into the very core of quantum computing, consciousness, and the arrow of time. It shapes how we model reality. It dictates what we believe can be known, remembered, or erased. In a world where black holes can merge, where two vast archives of cosmic matter and memory collide, what happens to all that information? Is it preserved? Or are the stories of entire galaxies erased with a whisper of Hawking radiation, as if they had never existed? That's the paradox, and it's far from solved. Event horizons, the skin of the void, the event horizon of a black hole is often described as its surface, but that's misleading. It's not a wall. It's not a solid boundary. It's not even a place in the traditional sense. It's a threshold, a point of no return, and once crossed, nothing, not even light can escape. But the deeper we dive, the stranger this surface becomes. It's more than just a barrier. It's a cosmic veil, where space and time flip roles, where gravity wins its eternal tug-of-war, and where reality itself begins to fracture. So, what is the event horizon really? Defining the horizon, not where, but when. Let's start with the basics. The event horizon is the boundary beyond which events can no longer influence an outside observer. If you stood just beyond the horizon and screamed, your voice wouldn't escape, not because the black hole is sucking things in like a vacuum, but because spacetime itself is falling inward faster than light can move outward. Think about that for a moment. You're not being pulled in by a force. You're standing still, but the very fabric of reality beneath your feet is collapsing inward at superluminal speeds. It's like standing on a waterfall of spacetime, with no way to climb back up. To an outside observer, you appear to freeze. At the horizon, your light gets redshifted, dimmer and slower, until you vanish into the void. But from your perspective, you fall in. You don't feel anything special at the horizon. You just continue on, unaware that the universe behind you has already written you off. This is the duality of the event horizon. Simultaneously the most important surface in the universe, and completely unremarkable to the falling traveler. Is the horizon a real surface? So, if you can't touch it, and it has no thickness, is the horizon just math? Not quite. While the event horizon has no substance, it has properties. It has area. It can grow, shrink, and vibrate. And according to Hawking's black hole thermodynamics, it even has temperature and entropy. That's right, black holes have entropy, and the amount is proportional to the surface area of the event horizon, not the volume inside. This led to the profound realization that a black hole's information content is stored not in its volume, but on its boundary, just like a hologram. And this flips our understanding of space on its head. If everything that falls in stars, gas, data, even consciousness, is encoded on this mysterious boundary, then the event horizon isn't just a line in space. It's a memory screen, a firewall, a skin stretched taut across the edge of oblivion, where the universe records what it cannot allow to vanish. Firewalls and the quantum crisis. Now, here's where things get violent. To preserve information, some physicists suggested the horizon is not smooth. It's a firewall, a wall of high-energy particles that burns anything falling in, destroying entanglement and emitting encoded radiation instead. This firewall paradox rips a hole in Einstein's equivalence principle, which says, falling into a black hole should feel normal, not catastrophic. If firewalls are real, then the event horizon is a blazing furnace. If not, then the universe must hide information some other way. Neither answer is comfortable. Asterisk ripples in spacetime. How we heard the merger asterisk. It began as a faint whisper in the fabric of reality, a signal traveling for over 1 billion years, across galaxies and starfields, reaching Earth in a trembling murmur smaller than an atomic nucleus. But that whisper wasn't made of sound. It was a ripple in spacetime itself, a gravitational wave, born from the violent union of two massive black holes, spiraling into each other with unimaginable force. It was the soundtrack of a cosmic collision, recorded not with microphones, but with lasers and mirrors. On September 14, 2015, humanity finally heard what the universe had been trying to say all along. Black holes do merge, and they leave behind an echo that shakes reality itself. This is the story of how we heard the merger, and what those whispers told us about the most mysterious monsters in the universe. The birth of a signal that two black holes, one about 36 solar masses, the other about 29, had been orbiting each other for billions of years. As they danced, they released gravitational waves, subtle distortions in spacetime, but nothing strong enough to detect until the end. In the final seconds, they spiraled faster, closer, tighter, emitting stronger and more frequent waves as their orbits decayed. This phase is known as the surreal, and it's where most of the gravitational wave energy is emitted. Then came the merger. The two event horizons collided, fusing into a single, larger black hole. In a fraction of a second, 3 solar masses worth of energy were converted into gravitational waves, radiating out in every direction at the speed of light. And on that quiet morning in 2015, 2 observatories on Earth, LIGO in Hanford, Washington, and Livingston, Louisiana, picked up the signal. They called it GW150914. It was the first direct detection of gravitational waves in history, and it changed everything. How do you detect a ripple in space-time? Imagine a ruler so precise that it can measure the distance between 2 mirrors with an accuracy smaller than 1/10,000th the width of a proton. Now stretch that ruler across 4 kilometers. Place it in a vacuum, isolate it from every vibration on Earth, and fire a laser down its length. That's what LIGO is. It uses laser interferometry to detect the tiniest changes in distance. Changes caused by a passing gravitational wave stretching space in one direction and compressing it in the other. As the wave passed through Earth, it deformed space itself, making one arm of the LIGO detector slightly longer and the other slightly shorter. The laser light, bouncing back and forth, created a pattern that revealed the distortion. It didn't just detect the wave, it heard the chirp of a black hole merger, and that chirp carried information, the mass, spin, and distance of the black holes, and the confirmation that they had merged into one. And if 2 black holes merge, their event horizons merge too, fusing not just mass and gravity, but possibly entangled records of everything they've ever devoured. Does that merged horizon obey the same entropy rules? Does it preserve memory? Or does something get lost in translation? The holographic encoding some theories go even further. What if the event horizon stores everything in a lower dimensional form, a 2D code representing the 3D reality inside? That's the holographic principle, and it suggests the entire interior of a black hole might just be a projection of the information stored on its surface. Think of it like a black box recorder, except the black hole is the recorder, and its skin, the event horizon, holds the encrypted summary of its entire history. And when black holes merge, these skins collide, overlap, recombine. Imagine 2 cosmic vaults crashing together, their surfaces rewriting each other's data in real time, not unlike a violent data migration on a planetary scale. And what emerges? A new horizon, a new skin of the void, a new version of cosmic memory. The horizon is watching. The more we study event horizons, the more they resemble active participants in the drama of reality, not passive lines on a chart. They store entropy, they radiate heat, they may even record the collapse of stars and civilizations, preserving their essence in geometric code. And when two black holes become one, their horizons merge into a new singular threshold, rewriting what the universe knows and what it allows us to see. The event horizon may look like a border, but it might be a script, playing out the final act of everything that ever dared to fall. Asterisk, he shape of the wave, a fingerprint of death. Gravitational waves aren't random. They have shape, they have pattern, and they act like fingerprints, revealing the violent dynamics that created them. The waveform from GW150914 followed a distinct three-phase structure, in spiral, a rising frequency and amplitude as the black holes spiral inward. Merger, a sharp peak in the waveform, the instant the horizons collide. Ring down, a fading signal as the new black hole settles into its final shape. This last phase is like the reverberation of a bell, spacetime itself ringing until it goes silent again. By analyzing the waveform, scientists could reverse engineer the event, like crime scene investigators piecing together a murder from the echoes of the final blow. They confirmed the black holes were non-spinning, and far older than our solar system. The remnant black hole was around 62 solar masses, with 3 missing radiated away as pure gravitational energy. The music of the universe. One of the most mind-bending revelations of gravitational waves is that they're audible, not in the air. They don't make sound in space, but when their frequencies are converted into sound waves, they become audible chirps, low to high, like a bird's call or a heartbeat accelerating. In other words, we don't just see the universe anymore, we hear it, and the first sound we ever heard was a black hole merger. The final death spiral of two massive objects colliding at half the speed of light. It's a moment that reshaped not just physics, but humanity's connection to the cosmos. Asterisk, what the wave told us. That single signal revealed more about black holes than decades of indirect observation. That black holes can form binaries and merge. That gravitational waves exist and travel across the universe, unimpeded. That general relativity holds true even in extreme conditions. And that the unseen universe is vast, violent, and waiting to be heard. It also proved that we were entering a new era of astronomy, one not limited by light, but expanded by gravitational hearing. Since 2015, dozens of additional signals have been detected, not just from black holes, but from neutron star collisions, hybrid systems, and potentially primordial relics from the early universe. Each wave is a story, a death, a birth, a transformation. Each is an echo of something we were never meant to witness. But now we can listen. Asterisk, merging realities. The dance before the collision, before two black holes collide, before the firestorm of gravitational waves and the fusion of singularities, there is a dance, a cosmic ballet, a spiraling, decaying orbit, so elegant, so precise, that it seems choreographed by the universe itself. For millions, even billions of years, two invisible titans circle each other, drawing closer with each pass, locked in an embrace that defies space, time, and reason. This dance is not gentle, it is violent. The black holes orbit at relativistic speeds, warping spacetime around them, dragging everything, even light, into their twisting maelstrom. And as they spiral inward, they radiate away energy in the form of gravitational waves, slowly bleeding momentum until the moment of no return. This moment, the final 3 seconds before the merger, is where the universe shows its cards, and what we find is more bizarre than anything fiction has ever dared to imagine. The relativistic spirals, the black holes get closer, their orbital velocity increases dramatically. Near the end of the in-spiral phase, they are moving at half the speed of light, over 150,000 kilometers per second. At that speed, Newton's laws no longer apply. We enter the realm of Einstein's general relativity, where time dilates, mass increases, and the fabric of space-time twists, like a vortex, to an outside observer. Time around the black holes seems to slow down, especially near the event horizon. From one black hole's perspective, its partner begins to appear distorted, stretched, redshifted, smeared across its own gravitational lens. This relativistic warping causes bizarre visual phenomena. The black holes mirror each other, creating looping reflections of their own warped horizons. You would see multiple versions of each black hole orbiting ghosts, chasing themselves across bent light paths. The closer they get, the more extreme these effects become. Reality begins to fold in on itself. Frame dragging and twisting. Either black hole is spinning, and most are. It begins to drag space-time along with it. A phenomenon called frame dragging. Imagine placing a marble on a stretched rubber sheet and spinning a bowling ball in the center. The marble won't just orbit, it'll spiral inwards, pulled by the twisted surface beneath it. That's what spinning black holes do to space-time. When two spinning black holes orbit each other, they create a tangled, dynamic field where the very axes of space and time are no longer fixed. This results in precession, a wobbling of the orbital path, and can even flip the orbital plane, causing the black holes to orbit in increasingly chaotic trajectories. The merger isn't a simple spiral. It's a warped, spinning, twisting collapse of geometry itself. The final three orbits just before the collision. The black holes complete their last three orbits in under 1 second. The gravitational wave, frequency spikes, the amplitude peaks. This is known as the chirp, the rapidly rising tone that signals imminent merger. Each orbit emits more gravitational radiation than all the stars in the observable universe combined. For a split second, the black holes are now so close that their event horizons begin to touch. Not collide, touch, and once they do, the rules change. Horizon to horizon, the event horizon is not a solid surface. It's a mathematical boundary, the point of no return. But when two black holes merge, their horizons don't collide like billiard balls. They flow into each other like drops of ink, merging in water. There is no flash of light, no explosion, just the smooth coalescence of two voids into one larger void. This process is governed by the no-hair theorem, which states that the final black hole will be defined only by three properties: mass, spin, and charge. Everything else, the complexity of the dance, the individuality of each black hole, is erased. Only the final result remains, and yet, the gravitational waves preserve the memory. They are the music of the merger. Entanglement and quantum shadows in the final instance before merging. A strange possibility arises. What if black holes are not just classical objects, but quantum systems? Recent theories suggest that black holes may carry quantum entanglement, information across their horizons, that their very structure is laced with hidden data. If true, then the merger may not just be a collapse of mass, but an entanglement of quantum states. The new black hole might inherit more than just mass and spin. It might inherit memory. This is related to the black hole information paradox, the question of whether information that falls into a black hole is truly lost. Some theorists argue that during mergers, these entangled states may interfere, or even create detectable echoes in the gravitational wave signal, faint deviations that reveal quantum structure in spacetime itself. We haven't found them yet, but the search continues. The mask of symmetry after the merger. The new black hole stabilizes and becomes almost perfectly symmetrical. Its event horizon becomes spherical. Its spin becomes constant. It no longer emits waves. It is silent. But beneath this symmetry lies a chaotic origin, the memories of billions of years of orbits, collisions, spin alignments, and space-time warps, like a mask covering a scarred face. The new black hole hides the complexity of what came before. All we're left with is the echo, The formation of a new black hole. Birth from collision. It is one of the most majestic and terrifying births in the cosmos, the creation of a brand new black hole, forged in the fiery grip of collision, sealed by gravity so strong that nothing escapes, not even the memory of what existed before. When two black holes merge, the outcome is not just a fusion of mass. It's a transformation of identity, a death and rebirth that defies our understanding of reality. The universe doesn't scream, it doesn't explode. It whispers in gravitational waves, and in those waves, encoded in ripples of spacetime itself, is the story of how the new singularity was born. The final plunge, event horizon, engulfment. Let us step back into that final moment. Two black holes, orbiting each other at nearly half the speed of light, spiral inward until their event horizons overlap. At this point, the individual identities of each black hole vanish. Mathematically, the merger creates a common apparent horizon, a surface that envelops both black holes and quickly settles into a single, smooth boundary. From the outside, it appears as if the universe simply rearranged its geometry in an instant. This new event horizon is dynamic, unstable, and larger than the sum of its parts. Why? Because part of the total mass and energy from the original black holes was radiated away as gravitational waves, a process that actually causes the final black hole to be less massive than the simple addition of its components. This birth is violent but strangely elegant. The laws of general relativity hold firm. The new black hole forms, and it rings. Quasi-normal ringing. The sound of creation. The newborn black hole does not immediately settle. Instead, it vibrates. It oscillates in a phenomenon known as quasi-normal ringing. Much like a struck bell, these oscillations are not sound. They are pure distortions of spacetime, releasing final bursts of gravitational radiation. As the black hole stabilizes, the ringing frequencies are determined by the final black hole's mass and spin, making them a kind of cosmic signature, a fingerprint left behind by the merger. Physicists can listen to these signals through detectors like LIGO and Virgo, extracting the mass and spin of the resulting black hole with astonishing precision. It's as if the black hole is announcing its arrival, not with light, not with voice, but with gravity itself. Energy budget. What gets lost? Not all mass survives the merger. A significant portion of energy, sometimes as much as 5% of the total system's mass, is converted into gravitational waves. That's more energy than our sun will emit in its entire 10 billion year lifetime, released in just a few milliseconds. To put that into perspective, in the first detection of a black hole merger, GW150914, about 3 solar masses worth of energy was radiated away in gravitational waves. 3 suns, gone. Not destroyed, not exploded, transformed into pure spacetime ripples. The remaining mass collapses into a stable singularity, surrounded by a smooth event horizon, and then silence, spin, and recoil, a twisted outcome depending on the spin orientations of the original black holes. The final black hole might rotate, sometimes very rapidly, if both original black holes were spinning in the same direction as their orbit. The final spin can approach the maximum limit, occur black hole with a spin parameter near 1. But here's where it gets even stranger. If the merger was asymmetric, say, if the two black holes had unequal mass or opposite spins, the final black hole experiences a kick. This is called a gravitational recoil, like a gun recoiling after a shot. The final black hole is propelled through space by the anisotropic emission of gravitational waves. Some black holes can be kicked at speeds exceeding 5,000 kilometers per second, fast enough to escape entire galaxies. This is not theoretical. Astronomers have identified candidates for such rogue black holes wandering intergalactic space, remnants of violent mergers long past. Even in birth, black holes do not rest. Thermodynamics of the new horizon. Once the final black hole stabilizes, its event horizon becomes its defining feature. But what does that mean, thermodynamically? Thanks to Stephen Hawking and Jacob Bekenstein, we know that black holes obey laws of thermodynamics. The area of the event horizon never decreases, analogous to entropy increasing. The surface gravity is constant like temperature. Energy can't be extracted without increasing the horizon area like the second law. So, the birth of a new black hole is also the creation of a new thermodynamic system. Its entropy is proportional to the area of the event horizon, and since that area grows with mass, larger black holes are more disordered. But disorder doesn't mean chaos. It means information, encoded in ways we still don't understand. Information puzzle deepens. Here lies the paradox. If black holes erase all distinguishing features of what fell into them, what happens to information? When two black holes merge, is the data about their previous interactions, their individual structures, quantum states, and entanglements, truly lost? Or is it somehow hidden within the geometry of the resulting black hole? This is the black hole information paradox, and the merger of two black holes is the ultimate test case. If information is lost during merger, it violates unitarity, a core principle of quantum mechanics. Some physicists argue that soft hair, quantum features on the horizon, may preserve this data. Others suggest that holographic principles, or E=E, PRA proposed link between entanglement and wormholes, may offer a solution. But for now, the mystery remains. The newborn black hole is silent. And yet, it may know everything. Echoes in the dark, detecting the aftershock of a merger when two black holes collide. The moment of their union creates a ripple, not just in spacetime, but in the very fabric of reality itself. The waves that radiate from this titanic event do not end with the initial burst. Some physicists suspect there may be echoes, subtle, ghost-like repetitions of the original wave, bouncing through the void like memories of a cosmic drumbeat. What if those echoes carry clues to what truly happens inside a black hole? What if they hint that black holes aren't quite what general relativity claims? What if they reveal the quantum truth of spacetime? The hunt for gravitational wave echoes. Since the first detection of a black hole merger in 2015, scientists have pored over the data from LIGO and Virgo, looking for something unexpected. Gravitational waves from a black hole merger typically show three stages. In spiral, two black holes orbiting, losing energy. Merger, the moment their horizons combine. Ringdown, the final black hole settling into a stable state. This ringdown is supposed to be a clean, exponential decay, like a bell losing its tone. But some researchers suggest there might be faint, repeating signals superimposed on the ringdown, a pattern of gravitational echoes, spaced milliseconds apart, decaying over time. These echoes would be impossible under classical physics. They might signal that the interior of a black hole isn't empty, that something exotic exists just beyond the event horizon. Exotic physics and quantum what could cause these echoes. One possibility is that black holes are not pure vacuum. Instead, they might have a quantum structure at or near the horizon. These include speculative concepts like fuzz from string theory, proposing that black holes are really tangled webs of strings with no true horizon. Gravastars, hypothetical objects with a quantum shell replacing the classical event horizon. Firewalls, violent quantum boundaries that destroy anything falling in. If any of these theories are true, then when gravitational waves hit the black hole's surface, they might reflect, creating a sequence of diminishing echoes. These would bounce between the core and the outer layers of the object, escaping slowly, like whispers from a dimension just beyond our own. Detecting such signals would be revolutionary, the first true glimpse of quantum gravity in action. Listening to spacetime, how we detect them, but how can we hear something so faint? Gravitational wave detectors like LIGO, Virgo, and CAGRA are sensitive to spacetime changes smaller than a proton's width. To detect echoes, scientists use techniques such as template matching, comparing observed signals with millions of possible echo patterns; wavelet analysis, breaking down the signal into its components to detect hidden frequencies; machine learning, training neural networks to identify faint, structured patterns buried in noise. The challenge is immense. Echoes are weaker than the primary wave, and the detectors themselves are noisy. Some teams claim to have found tentative evidence for echoes in existing data, but the results are not universally accepted. The debate rages on, but each new black hole merger gives us more data, more chances to eavesdrop on the universe's deepest secrets. Implications: if echoes are real, the consequences of confirmed gravitational echoes would be profound. It would imply that general relativity breaks down near the event horizon. It would give direct evidence that black holes are not entirely black. They reflect information. It would offer a way to resolve the black hole information paradox without violating unity in essence. Echoes would reveal that the boundary of a black hole is not a point of no return, but a quantum membrane, interacting with the universe in subtle, non-classical ways. It could be our first true evidence that gravity and quantum mechanics are part of a single, unified framework. Perhaps even evidence that spacetime itself is emergent, not fundamental. The cycle of echoes and cosmic memory there. Something haunting about the idea of echoes. They represent memory, the cosmos, remembering its own violence. Each gravitational wave is a story, and each echo a retelling. Fainter, softer, but still carrying the essence of what happened. These echoes might tell us the shape of the quantum landscape, the limits of Einstein's theories, the true structure of the vacuum. In some models, these echoes could go on indefinitely, like a black hole ringing not once, but forever, slowly revealing itself across cosmic time. Every merger might then be not an end, but a conversation, whispered across spacetime in a language we are just beginning to understand. Black hole, mergers, and the fabric of spacetime. Though collision of two black holes is more than an astronomical spectacle, it's a fundamental test of reality itself. When their gravitational fields entwine and warp into one, something happens to the very geometry of the universe. It's like watching spacetime being rewritten in real time. What does it mean for the fabric of reality to ripple, twist, and recover? What's this fabric made of? Really? Does it stretch forever? Can it tear? And when black holes merge, does the universe change permanently? Let's go deeper. What is the fabric of spacetime? Spacetime isn't a physical substance in the traditional sense. It's not made of atoms, particles, or energy. Instead, it's a mathematical arena in which all physical events happen. Einstein described it as a four-dimensional manifold, with 3 spatial dimensions and 1 time dimension, woven into a continuous, malleable whole. This fabric bends under mass and energy, causing gravity. A black hole is essentially a pinch in this fabric, a place where it curves so intensely that all paths lead inward. But when two such distortions merge, the result isn't just a bigger black hole, it's a fundamental remodeling of local spacetime. The merger event, as spacetime surgery. Think of spacetime as a stretched rubber sheet. A single black hole is like a bowling ball, creating a deep dimple in the sheet. Two black holes merging. It's like 2 bowling balls spiraling into each other. Their dents overlapping, the sheet stretching, warping, sometimes even vibrating violently. During the collision, the curvature becomes nonlinear, meaning 1 + 1 doesn't equal 2. The geometry flattens, sharpens, twists. Some regions become briefly curved, like knots forming in a rug being yanked from 2 ends for a fraction of a second. The fabric of the cosmos is in turmoil, and then a new black hole forms a single, deeper pit in the fabric. But what remains? Are there scars? Gravitational memory. The universe doesn't forget. Here's something wild. When a black hole merger ends, and the gravitational waves ripple outward, there is a residual effect called the gravitational memory effect. It's a subtle, permanent distortion in spacetime left behind by the passing waves. Imagine a field of particles floating in space. After the wave passes, they don't return to their original positions. They're permanently shifted, however slightly. This memory effect implies that spacetime remembers what happened. It's as if the universe itself was etched by the collision. Every merger, every ripple, permanently alters the structure of reality, like tiny strokes on the canvas of the cosmos. Quantum foam, beneath the fabric now. Go even deeper, zoom in below, Planck scales. Beneath the spacetime continuum, some physicists believe that, at these unimaginable scales, spacetime isn't smooth at all. It's made of quantum foam, a chaotic, frothing sea of micro-wormholes, fluctuations, and topological anomalies. Black hole mergers might not just warp spacetime at the large scale, but also stir the foam beneath, sending ripples into this quantum realm. If so, then these collisions could reconfigure the foundation of the universe itself. Imagine, if every black hole merger sends instructions to the vacuum commands that reshape the rules governing reality, ever so slightly. Could this explain dark energy? Could this affect the fine structure constant, or other physical laws? Some theorists dare to ask, could black hole mergers be part of a self-programming universe? Does spacetime tear? During the peak of a black hole merger, the curvature of spacetime approaches infinity. But does it break? Einstein's equations suggest no, but only if you ignore quantum mechanics. Some quantum gravity theories, like loop quantum gravity, suggest spacetime is made of discrete units, tiny loops, or atoms of space. In these models, a merger could temporarily push spacetime to the brink, creating quantum discontinuities, momentary tears, or reconfigurations that are quickly healed. Other proposals like string theory suggest that such events create topological transitions, like the universe flipping from one shape into another. We've never observed this, but we've never looked at these mergers with eyes sharp enough. Perhaps in the future, we'll detect a merger that doesn't just warp space, but fractures it. Consciousness and the geometry of time. Here's a philosophical turn. If black hole mergers reshape spacetime, and time is part of spacetime, does time itself change? Could a region of the universe experience a new temporal geometry after a merger? Could this explain anomalies like cosmic acceleration or temporal asymmetries? Some speculative thinkers go further, suggesting that consciousness itself is somehow tied to spacetime geometry, a controversial idea, but one that gains intrigue when we consider the scale of change a merger produces. If black hole collisions change time's flow locally, could they, however, minutely affect the conditions for consciousness somewhere in the universe? Are these mergers not just cosmic events, but ontological ones reshaping existence at all levels? Final thought. Are we living in a merged universe? Here's the final twist. What if our own observable universe is the result of a black hole merger on a scale beyond comprehension? Some versions of the multiverse hypothesis suggest that new universes are born when black holes collapse in other universes, a process called cosmogenic black hole theory. If so, every black hole merger could be creative, not destructive, and maybe, just maybe, the Big Bang itself was the result of two primordial black holes merging in some deeper meta-universe. In that case, when we observe black holes colliding, we are watching a creation myth, a story the universe keeps telling, again and again. Asterisk information, entropy, and the secrets hidden in the merge. When two black holes merge, it's not just gravity that's involved, it's information. What do the black holes know before they merge? What happens to that knowledge after? And does anything get lost forever? These questions strike at the heart of one of the most famous puzzles in modern physics, the black hole information paradox. And during a merger, that paradox gets supercharged. Let's open the vault. What is information in physics? In everyday terms, information means facts, data, knowledge. But in physics, information is the precise description of a system's physical state, its particles, positions, velocities, quantum numbers, and more. In quantum mechanics, information is never destroyed. This rule, called unitarity, is sacred. It ensures that if we knew the exact state of the universe at one moment, we could, in principle, reconstruct every past and future moment. But black holes challenge that idea. The information paradox. Stephen Hawking famously proposed that black holes emit Hawking radiation, a faint glow that causes them to slowly evaporate. But this radiation, he argued, is random. It doesn't carry information about what fell in. So, when a black hole vanishes, all that infalling information about matter, energy, stars, astronauts, whatever disappears. Poof, gone. This violates quantum mechanics, and so, the black hole information paradox was born. Decades of debate followed. Merging black holes add a twist now. Imagine two black holes merging. Each contains its own store of entangled, encrypted quantum information bits of everything they've consumed. When they collide, the new black hole must contain all that information, but how? And what happens to redundant or conflicting data? Does it get scrambled, erased, or compressed? Is the process reversible? Even in theory, no one knows. But gravitational wave patterns might hold clues. The waves don't just tell us about mass. They may encode subtle hints about the entropy and structure of the merging holes. It's as if spacetime is trying to whisper the secret recipe of what just happened. The Bekenstein-Hawking entropy. Entropy. Every black hole has entropy, a measure of how much information it can theoretically store. This entropy is proportional to its surface area, not its volume, a deeply strange result. It suggests that the contents of a black hole are stored holographically on its event horizon. So, when two black holes merge, the new horizon must account for all previous entropy, possibly more. This means black hole mergers increase the entropy of the universe. Each collision is a cosmic upload, a step toward a more complex and entangled reality. But what's in that upload? What are we gaining or losing? Firewall or fuzzball? Some physicists propose that black holes might contain firewalls, searing walls of energy that destroy information at the event horizon. Others argue for fuzzballs, objects without a sharp event horizon, where information is preserved in stringy quantum states. Either way, black hole mergers could be the proving ground. If firewalls exist, merging black holes would unleash massive bursts of energy, not explained by gravity alone. If fuzzballs are real, the final black hole might emit non-thermal radiation, a kind of quantum signal embedded in the chaos. What LIGO and future detectors find might validate or destroy entire frameworks of quantum gravity. Information imprints in gravitational waves. Here's a wild theory. Gravitational waves could carry information content themselves, not just mass and spin, but something deeper. Some researchers believe the waveform's fine structure might encode echoes of quantum corrections near the event horizon. These echoes might tell us whether the black hole has a traditional horizon, whether information is trapped or bouncing, whether space-time is smooth or foamy if true. Future detectors like LISA laser interferometer space antenna might act like cosmic decryption machines, peeling back the data hidden in space-time vibrations. Could merged black holes become memory banks? Here's a far-reaching thought. What if black holes are not just destroyers of information, but curators? After a merger, the resulting black hole may compress vast quantities of entangled quantum states into a new, hyperdense configuration. Some theorists speculate that black holes could serve as natural hard drives, extremely efficient storage systems for universal history. And if this is true, could we, someday, read that information? Could future civilizations learn how to decode the spin mass, and wave pattern of a black hole and reconstruct the events that led to its formation. Imagine pointing a telescope at a black hole and watching a movie of the stars it consumed. Not fantasy, just very, very advanced physics. Consciousness, information, and mergers. Let's stretch reality further. Some thinkers believe consciousness arises from information patterns. If that's true, then could merging black holes' information factories on an unimaginable scale, briefly, generate emergent forms of awareness? Could there be a flicker of cosmic thought in the storm of entropy and geometry? No evidence supports this yet. But if information is never destroyed and if black hole mergers are information reshufflers, then perhaps they create strange, transient states of order, however brief. Not minds, exactly, but something close. The final ledger: is anything truly lost? After all this, we return to the paradox. When two black holes merge, and the gravitational waves fade, and the new event horizon forms, ... is anything truly gone? Or has everything been preserved, just in a radically transformed state? The laws of quantum mechanics demand preservation. The math of general relativity allows loss. And so, at the edge of the universe, in the split second of a collision, lies the answer to the deepest puzzle of existence. Not just how matter behaves, but whether the universe keeps its memories. The merge from inside, a hypothetical journey through the collision. What would it be like to witness the merger of two black holes from the inside? Impossible. Yes, but let's imagine. Let's hypothesize, stretching the laws of physics to their narrative breaking point. Just a peek inside a moment that no living thing could survive. Let's dive into the eye of the storm, where space folds, time twists, and everything familiar is swallowed whole. Falling toward the first horizon. Imagine you're in a specially constructed probe, built from exotic matter that somehow resists tidal forces, your last lifeline to observation. You're approaching a black hole as you near the event horizon. The curvature of space-time bends light into infinite rings. Behind you, the universe stretches into a distorted mosaic. Stars whirl, galaxies smear, colors shift toward deep reds. Time slows for you, speeds up outside. You fall, ... and cross the horizon. Nothing happens, at least not at first. General relativity says this crossing is silent, seamless. But your instruments register something chilling: causal disconnection. You can no longer communicate with the outside. You're now information inward bound with one destination. Inside the first black hole, contrary to popular belief. The interior of a black hole is not a simple void. It's a dynamic, complex structure shaped by mass rotation and possibly quantum geometry. As you fall inward, you enter a warped funnel spacetime, narrowing, tidal forces increasing. If this black hole spins a curved black hole, you might pass through layers of geometry, ergosphere, a region where space itself is dragged along with the black hole's spin. Outer horizon, the conventional event horizon. Inner horizon, a second boundary, unstable and potentially turbulent. Ring singularity, a rotating line of infinite curvature. The core. But you are not headed to the singularity. Not yet, because now the unimaginable happens. Another black hole is falling into yours. Collision from the inside. Your instruments detect violent disturbances ahead. The entire internal structure begins to shudder. Space-time itself is convulsing. Shockwaves of gravitational compression ripple through the geometry. The once static funnel begins to twist, churn, and collapse. Remember, black holes have no solid surface, only gravitational fields and space-time warps. But inside, this field is folding in on itself. The new black hole is tunneling into your own. You feel pulled, not just inward, but sideways, across dimensions that twist like Mobius ribbons. You're now between two collapsing coordinate systems, caught in the intersection of realities. Non-Euclidean chaos. All spatial logic breaks. Left and right lose meaning. Time runs in multiple directions forward, backward, sideways. Causal loops form and dissolve. Particles appear, vanish, and reappear elsewhere. Quantum fields fluctuate so violently your sensors register 10 degrees Kelvin temperatures beyond comprehension. This is the merger interior place no classical theory can describe. It's not space, it's not time. It's pure geometry in conflict. You witness structures resembling quantum foam bubbling, boiling subunits of space. Is this what Planck scale turbulence looks like? Or are you hallucinating? Your brain can no longer trust what it perceives, but your ship's clock still ticks, and you're heading toward the point of no return at the core of the merger. There's no center. Instead, there's an intersection of singular twisting knot of spacetime curvature. It's not a dot, it's a region one with higher dimensions. Unknown physics, maybe even a bridge. Some theories suggest that, at the moment of a merger, these internal structures briefly connect like wormholes, colliding in recombing. Others claim the singularities evaporate into quantum chaos, releasing data back into the universe via subtle, gravitational echoes. Your instruments scream with noise. Every axis flips. Your probe begins to disintegrate not from force, but from informational decoherence. Reality is no longer coherent. Your atoms can't agree on where they are. Your mind, held together by algorithms, begins to drift. You are dissolving into the quantum heart of the merger, just before your last sensor fails. It records something incredible, an information pulse, faster than light, not in space, but across space-time topology, a brief emergence of negative energy density, a ripple pattern that looks like a signature, a repeatable structure, as if the merger contains code. Instructions. A cosmic logic function, executing itself. You realize, the merger isn't just a collision, it's a computation. The black holes are calculating what? Unknown, but perhaps black. Hole mergers are fundamental processing events of the universe compressing, updating, reconciling data about matter, energy, and geometry. You are now a part of that process. Aftermath and echo from the outside. This entire journey takes a fraction of a second. A burst of gravitational waves shoots out into space, carrying whispers of your final observations. The universe shudders, then calms. But inside, you experienced eternity's a slow-motion fall into the deepest well of reality. You are now encoded in the spin, mass, and gravitational memory of the resulting black hole. Your story, your signal, may someday be rediffed. The universe ever learns to decode the language of the singularity. Until then, your echo rides the curvature of space. Waiting. How? The universe uses mergers to evolve at first glance. A black hole merger seems like a cosmic catastrophe, two monstrous gravitational wells colliding, obliterating anything in their way. But what if, instead, it's an essential mechanism, a feature, not a bug of the universe's grand operating system? In this final subtopic, we explore the philosophical, physical, and cosmological role that black hole mergers may play in the evolution of reality itself. Beyond destruction, a creative force, universe operates through cycles of collapse and rebirth. Stars burn out, galaxies collide, atoms fuse and split, and black holes merge. Every time a merger occurs, a few things happen. Gravitational waves ripple outward, reshaping space-time on a cosmic scale. Mass energy configurations are rearranged, creating more massive black holes, potential seeds for future quasars or galaxy cores. Information is compressed, encoded, and redistributed through gravitational memory. In other words, a merger isn't just an end, it's a transition point, a rebirth in disguise, much like how a supernova seeds the galaxy with heavy elements. A black hole merger might seed the geometry of the universe with new topologies, reshaping the curvature of space for eons to come. Cosmic memory. Storing the past in mass. One of the most intriguing theories in modern physics is the idea that black holes don't destroy information. Instead, they store it. And when they merge, that data, every photon, quantum field, and particle they've absorbed, gets scrambled, but not deleted. The final product, the merged black hole, encodes this massive library of absorbed history into its mass spin-charge gravitational wave signature. So, when two black holes collide, they're not just combining matter, they're merging timelines. The final gravitational wave signal is not just a sound, it's a syllable in the language of the cosmos. Spoken across billions of years, its memory becoming structure. Mergers as cosmic computations. Some theoretical physicists, particularly those inspired by digital physics and emergent spacetime theories, have proposed that the universe functions as a quantum computer. In this view, particles are bits, forces are logical operations. Spacetime is the substrate, and black hole mergers, they're processing events. High-energy, ultra-dense collisions, where massive quantities of data are collapsed into simplified forms, rewritten under extreme gravitational laws, transferred into future causal structures. From this perspective, every merger is like a hardware upgrade to the universe's simulation, optimizing entropy, refreshing fields, and reinforcing causal coherence. They are the big saves in the universe's memory system. Evolution of complexity. Let's return to a broader idea. Evolution. Not just of life, but of cosmic complexity. Stars evolve, planets evolve, life evolves, but so does structure and laws. Black hole mergers can trigger galactic realignments, stimulate new star formation through feedback mechanisms, lead to the creation of binary remnants, or even gravitational wave turbulence that seeds the cosmic microwave background with subtle updates. Each merger is a pivot point, a reorientation of large-scale gravitational frameworks that shapes the future evolution of everything downstream. They guide how galaxies form, where matter clumps, and how time flows. They're the universe's version of tectonic shifts, silent, massive, foundational, asterisk. The future of observation. Now that we can hear these mergers through gravitational wave detectors like LIGO and Virgo, we're entering a new era of astronomy. Soon, with even more sensitive instruments like LISA, we'll detect intermediate black hole mergers, primordial black hole collisions, exotic gravitational anomalies. This will open a window into the deepest past, moments when the universe was minutes old, or even pre-Big Bang. If some theories hold, every merger we hear is a lesson, a line in the autobiography of the cosmos. We just have to learn the grammar. And what about the far future? As stars die and galaxies dim, black holes will become the last architects of structure in the universe. Billions of years from now, black holes will continue to orbit, collide, and merge. These final mergers will echo through the cold, dark future, each one reshaping the dwindling geometry of existence. Eventually, even these massive entities may evaporate through Hawking radiation, releasing their information into the void. Eventually, even these massive entities may evaporate through Hawking radiation, releasing their information into the void. But their imprint, the scars of their mergers, will remain. In the curvature of spacetime, in the distribution of cosmic background, in the final thermodynamic balance of the universe, the last fireworks of a fading cosmos. Final thoughts. The mergers as messages. What if every black hole merger is a message? Not from aliens, but from the universe itself. A signal that says something happened here. Something profound. Mass met mass. Energy reshaped energy. And the rules of everything flexed. Just a little. To study mergers is to read the margins of the cosmos, the notes scribbled in the folds of spationing. And in those folds, perhaps, we'll find not just answers, but invitations to wonder, to listen, to evolve. Asterisk. The dance of three. What happens when a third black hole joins the merger? We've looked at the collision of two black holes, a binary system destined to spiral in, crash, and merge. But what if a third black hole joins the waltz? In the grand halls of the cosmos, such a thing isn't just possible, it's inevitable, especially in dense galactic cores, where black holes may orbit close enough for gravitational influence to spiral out of control. Here begins a tale of chaos, geometry, and gravitational betrayal. Asterisk the three-body problem. Relativistic in classical mechanics. The three-body problem is notorious. Given three masses and their gravitational influence on each other, it's nearly impossible to predict their precise motions over long periods. The system becomes chaotic, sensitive to even the tiniest changes in starting positions or velocities. Now imagine the same, but with bodies that bend spacetime itself, velocities near light-speed warped orbits, relativistic time dilation, and gravitational radiation. In this relativistic chaos, the trio of black holes do not orbit peacefully. Instead, one may be slingshotted outward, ejected from the system at breakneck speeds. The remaining two may tighten their spiral, merging rapidly, or all three might enter a brief, frenzied dance of mutual death, ricocheting through warped space-time. This scenario isn't just rare, it's unpredictable, unreadable, and unbelievably violent. Gravitational slingshots, ejections at the edge of light. When three black holes interact closely, one is often ejected. The reason? Energy conservation. When two black holes draw tightly together, the gravitational binding energy of their union increases dramatically. The excess energy has to go somewhere, and that somewhere is often into the third body. The result? That third black hole is flung out, sometimes at a significant fraction of the speed of light. We call this a gravitational recoil, and it creates rogue black holes hurtling through intergalactic space, orphaned singularities that carry the memory of a failed merger, unique gravitational wave signals that sound like a symphony. Interrupted mid-nogene, a supermassive black hole, ejected from the center of its galaxy, wandering the cosmic desert, invisible yet immense. It's not science fiction, it's a known possibility. Entropy in triplicate. Every black hole has entropy. It's related to the area of its event horizon. The bigger the surface, the more entropy. When two black holes merge, the result has more entropy than the sum of its parts. That's consistent with the second law of thermodynamics, but in a triple system, things get tricky. Entropy can be lost temporarily if one BH is ejected, redistributed strangely if all three enter chaotic orbits, amplified if the final merger creates a rapidly spinning, high-energy remnant. Physicists speculate that three-body black hole systems may represent an entropy-optimization mechanism in the universe, a way to rapidly increase complexity and disorder, paving the way for greater information storage within spacetime. In other words, when black holes play in threes, the universe learns faster. Triple mergers and quantum paradoxes here. Where things get really weird. Imagine three black holes that each contain information, the memories of the matter they consumed. Now let's say they all merge in a chaotic fashion. What happens to that information? Is it scrambled beyond recovery? Is it layered into a larger emergent system with fractal complexity? Does it form quantum interference patterns, echoing across the gravitational waves? Some physicists believe that triplet interactions may hold the key to solving the black hole information paradox, because the added complexity creates non-trivial topology inside the event horizon. Translation: the interior of a triple black hole might not just be a sphere, but a knot of spacetime, capable of preserving quantum entanglement in ways we don't yet understand, a cosmic Rubik's Cube, constantly solving and reshuffling itself. Can we detect a triple merger? Not yet. Current gravitational wave detectors like LIGO and Virgo are tuned for binary mergers, clean, elegant collisions with a predictable waveform, but a triple merger, That would create asymmetric waveforms, glitches, and echoes, chaotic frequency spikes. In fact, scientists may already have recorded signals that don't quite match binary patterns and dismiss them as noise. With next-generation observatories like LISA and the Einstein telescope, we may soon be able to decode the dance of three, hearing, for the first time, the wild roar of a triad merging in rage. Imagine that, a symphony of distortion, playing out across the void. Final thought for this segment: when two black holes merge, the result is majestic. But when three try, it becomes a tragedy, or perhaps a comedy of cosmic chaos. Either way, the rules change, the orbits shift, the future branches wildly, and in that moment, just before entropy wins, the universe holds its breath. Because the dance of three is not just physics, it's art. Let me know if you'd like to continue with subtopic 1.17 and beyond. We can keep exploring advanced ideas like, can black hole mergers open gateways to new dimensions? Do black hole collisions affect the arrow of time? What do black hole mergers look like from inside the event horizon? Asterisk, can a black hole merger open a gateway to another dimension? It's a question that pulls at both scientific minds and science fiction hearts. When two black holes collide, unleashing gravitational waves that ripple across the cosmos, bending time itself, could something else happen? Something not just violent, but transformative? Could the merger of two immense singularities open a door to a new dimension? Let's explore that idea, not with speculation, but with the bleeding edge of theoretical physics, where general relativity and quantum mechanics begin to blur into mystery. The fabric of spacetime isn't flat, it's a looped landscape. Imagine the universe not as a blank canvas, but as a warped, elastic membrane, a four-dimensional sheet of spacetime that can twist, ripple, stretch, and even fold. When two black holes merge, they cause one of the most extreme deformations of this fabric possible. The gravitational waves that result are literal tears and tremors in the medium that defines existence. Now ask, what happens when that fabric is bent so tightly, at such high energy, that it begins to interact with itself in extra-dimensional ways? Some physicists suggest that under conditions of extreme spacetime curvature, like a black hole merger, the geometry of space could pinch or fold in ways that allow for the temporary overlap of distant points, a bridge, a loop, a gate. And this is where extra dimensions come in. String theory and the hidden dimensions of reality. According to string theory, the universe has more than just the familiar 3 + 1 dimensions. There may be 10 or even 11 total dimensions, most of them curled up, folded so tightly we can't perceive them. But what if a black hole merger creates the conditions necessary to access or briefly interact with these hidden dimensions? When two singularities combine, the energy density and curvature of spacetime can become so extreme, they might punch through the thin veil separating the visible universe from its hidden companions. Think of it like rubbing your hands together until the friction burns a hole in your gloves. In this case, the gloves are spacetime itself. Wormholes, fiction or emergent phenomenon. You've heard of wormholes, theoretical tunnels through spacetime, sometimes called Einstein-Rosen bridges. They're mathematically valid solutions to Einstein's field equations. But there's a catch. They usually require exotic matter material with negative energy density to stay open. And here's the twist. Some researchers believe the extreme energy and curvature of a black hole merger might mimic the effects of exotic matter, allowing a transient wormhole to naturally form at the moment of collision. It wouldn't be stable. It wouldn't be safe. But it might exist for a flickering instant, long enough to link to distant points, or even to different universes. From the outside, you'd see a spike in gravitational wave data, a signal with no echoes or unexpected decay rates. From the inside, well, no one knows, because no information can escape from within a black hole, unless, of course, That's exactly what a wormhole allows. Do colliding black holes create quantum portals in the framework of loop quantum gravity? Another contender for a theory of everything. Spacetime is quantized, made of tiny loops that interlock to form reality. In this view, the Planck scale structure of spacetime could be disrupted during a black hole merger, forming a non-local interaction, effectively a quantum shortcut to somewhere else. Physicists call these speculative phenomena quantum bridges. They might connect to distant regions of the same universe, link a black hole's interior to a white hole elsewhere, or function as a one-way passage into a parallel brane, another 4D slice in the higher dimensional multiverse. It's not science fiction. It's the frontier of real theoretical physics, and it's being modeled on supercomputers as we speak. Could we ever detect a dimensional shift? Let's be clear. We can't detect other dimensions directly, but we can look for anomalies in the signals we already observe. For instance, a black hole merger that violates energy conservation on our side of the universe might be leaking energy into another dimension. An unusual delay or asymmetric waveform in gravitational wave patterns could signal that something interfered with the merger from beyond our 4D reality. A post-merger object that seems to have less mass than expected might be evidence that some of it went elsewhere. Leo and Virgo haven't seen such anomalies yet, or have they? Some signals do show echoes or decay behaviors that don't fully match predictions. In 2020, a team of physicists even suggested that gravitational wave echoes could be signs of new physics beyond general relativity or dimensional leakage. It's controversial. It's fringe, but it's not impossible. The echo chamber of reality if two black holes merge and a wormhole opens. Even briefly, could it reflect information? Some theorists believe the merger might not just create a passage, but an echo chamber, a place where signals bounce back and forth between dimensions before dissipating. This could explain certain post-merger gravitational wave anomalies, like faint secondary signals, arriving milliseconds or even seconds later, with distorted frequency bands. In this view, the black hole merger doesn't just end in silence, it ends in resonance, a whisper echoing through the walls of reality. Final thought for this segment: black hole merger is not just a collision. It's not just a ripple in spacetime. It may be the cosmic equivalent of knocking hard on the walls of the universe, and perhaps, on the other side, something knocks back. Are we prepared to listen? Do black hole mergers affect the arrow of time? Time flows forward, or so we believe. From birth to death, sunrise to sunset, time feels like a one-way street. But does the universe agree? And what happens to that direction, that arrow of time, when two black holes collide? It's a question that touches the deepest parts of physics, from thermodynamics to quantum entanglement, and from entropy to the very nature of reality itself. Let's journey into the place where time might not just tick, but twist. What is the arrow of time? Let's define it properly first. The arrow of time is a term used to describe the one-directional flow of time, from past to future. But here's the mind-bending twist. The laws of physics are almost entirely time-symmetric, whether you're solving Newton's equations, Schrödinger's wave function, or Einstein's field equations. They work both forwards and backwards. So why does reality feel like it only runs one way? The answer lies in entropy. Entropy, the master clock of the universe. Entropy is a measure of disorder. The second law of thermodynamics says that in a closed system, entropy always increases, meaning things move from order to chaos, not the other way around. A glass shatters, but never unshatters. You grow old, but never young again. Stars burn out, but never reignite spontaneously. This progression of entropy is what defines our experience of time. So, now ask, what happens when two black holes merge, the most entropic, chaotic event in the known universe? Black holes have temperature and entropy. In the 1970s, Stephen Hawking shocked the world by showing that black holes aren't entirely black. They emit radiation, and they have temperature. And crucially, entropy. A black hole's entropy is proportional to the area of its event horizon, not its volume, a revelation that hinted at the holographic nature of reality. So when two black holes merge, their combined event horizon area increases, and so does their total entropy. This means the merger is a thermodynamic event, one that drives the arrow of time forward. The universe becomes more disordered, not less, and that's just the surface. The merger as a temporal asymmetry catalyst. If we could somehow observe a black hole merger in reverse, the event would violate known physics, because the entropy decrease would mean energy and information are being uncertain, something we've never seen happen naturally. In other words, black hole mergers are irreversible. They're not just events in time, they're anchors of time, moments where the flow of time is cemented, amplified, and undeniable. Every merger is a cosmic fingerprint of the irreversibility of the universe. Time reversal symmetry broken. In quantum mechanics, time reversal symmetry is baked into many equations. But some phenomena, like CP violation, charge parity violation, already hint that time symmetry isn't perfect in the quantum realm. Now consider that a black hole merger is the most violent, energetic quantum gravitational event we can detect. Could it break T-symmetry even further? Could it create zones of temporal deformation, where time stretches on one side of the singularity and compresses on the other? Or even reverse, if observed from certain extra-dimensional perspectives? It's a possibility being modeled with quantum gravity simulations, and some of them show fascinating results. Closed time-like curves and temporal loops. If extreme gravity can bend space, it can bend time. In the aftermath of a merger, the distortion of spacetime is so intense, it could allow the formation of closed time-like curves, CTCs, paths through spacetime that loop back on themselves. In theory, you could travel along a CTC and arrive back at your starting point, not just in space, but in time. Some physicists argue these might appear very briefly during the transition state of a black hole merger, particularly if quantum geometry allows for temporary micro-wormholes. Would that mean a localized reversal of time? Maybe not one you could experience, but one that affects the math, and perhaps affects the flow of cause and effect itself. Gravitational waves and time signatures. Gravation wave detectors like LIGO record time-stamped space-time distortions. Interestingly, some of these waves show asymmetric shapes, steep rises, long decays, or subtle echoes that arrive after the main event. Physicists are exploring whether these asymmetries reflect time distortion near the merging black holes. Some waves might have been stretched, others might have looped, some may have experienced a nonlinear temporal shift due to extreme spacetime curvature. In essence, the waves themselves might be telling us that time didn't behave normally near the merger site. Could observers experience different time flows? Here's a scenario. A spacecraft sits a safe distance from a black hole merger, observing it from a few light years away. Another ship plunges toward the event horizon just before the collision. For the distant ship, the entire event lasts just a few seconds. For the ship approaching the singularity, time slows down, possibly to a standstill. In this case, the same event has different durations, depending on your position in the gravitational field. This is not speculation, it's general relativity. And it shows us that the arrow of time isn't universal. It's personal. It's relative. Final questions. Could time be reset? What if the merged black hole forms a baby universe inside it? One where the arrow of time begins anew, fresh, unwritten, unbound by our entropy. If true, then black hole mergers are not just time drivers, but time rebirthers, events where the clock doesn't stop. It restarts. In that case, every merger is a cosmic Big Bang, somewhere else, a temporal reboot, a fresh beginning, a new universe, with its own arrow of time, and we're just watching one tick of the multiversal clock. Asterisk, could merged black holes influence consciousness? This may sound like science fiction, but some of the most respected physicists and neuroscientists have started exploring a controversial, fascinating question. Could consciousness, the inner theater of your mind, be influenced by massive cosmic events like black hole mergers? Could there be a link between gravity, quantum entanglement, and the emergence of self? Or, to put it more boldly, could the collision of two black holes create a gravitational shockwave so powerful, so exotic, that it interacts with the fabric of perception itself? Let's journey down this strange and speculative road, where neuroscience meets relativity, and black holes might whisper to the soul. What is consciousness? First, let's define the beast. Consciousness is the state of being aware of oneself, of the external world, of thoughts, time, emotion, pain, hope, memory. But what creates this awareness? No one knows. We understand how neurons fire, how brain chemistry works, how sensory data is processed. But the subjective experience, the you behind your thoughts, remains a mystery. This is called the hard problem of consciousness, and it's unsolved. Could black holes, the most extreme objects in the universe, offer a clue? The gravity consciousness hypothesis. Here's a strange idea. Some physicists, including Roger Penrose, have proposed that gravity might play a hidden role in the collapse of quantum states in the brain, possibly giving rise to conscious awareness. According to this theory, called orchestrated objective reduction, or COR, microtubules in neurons are the site of quantum computations, and gravity helps decide when a quantum state becomes real. So imagine this. If gravity is influencing consciousness at the quantum level, then an extreme space-time distortion, like a black hole merger, could ripple through space and nudge that process, even if subtly. In other words, massive gravitational waves might interfere with how consciousness emerges in living systems, not to control it, but to resonate with it. Our brain's antennas for cosmic vibration. There's an ancient idea, echoed in Hinduism and echoed again in speculative physics, that the mind is not the producer of consciousness, but the receiver of it. If true, that would mean consciousness is non-local. The brain is a filter, not a generator. Gravity waves could affect how we tune in to consciousness, and black hole mergers. They generate the largest gravitational waves the universe has ever produced. Some scientists have proposed, though without hard evidence, that certain biological systems, perhaps highly ordered water molecules or brain could be sensitive to these cosmic ripples. Could black hole mergers briefly shift brain states, subtly changing dreams, emotions, or insights, even across billions of light? A wild idea. But the math isn't entirely impossible. Time dilation and the perception of consciousness. What we perceive as the flow of thought, one idea following another, is deeply tied to our sense of time. Now imagine a black hole merger close enough to our solar system to cause gravitational time dilation, not enough to kill, but enough to slow down the processing rate of the brain. You could experience 30 seconds of thought in what the external universe registers as 1 second. This would feel like time slowing down, the world becoming still, a strange surge of clarity or expanded awareness. And while we haven't had such an event in human history, if one occurred within our local galactic neighborhood, we might collectively feel it in dreams, in focus, in strange awakenings. Collective consciousness and cosmological entanglement. Carl Jung once spoke of the collective unconscious, a hidden substrate of shared memory and symbolism across human minds. What if, on a quantum level, all conscious beings are slightly entangled? And what if the merging of black holes, which rearranges the space-time substrate, slightly reconfigures the entanglement map, even subtly? This could result in sudden global patterns of similar dreams, spontaneous emotional shifts in populations. bursts of creativity or existential reflection across cultures. It may sound strange, but studies have documented worldwide emotional fluctuations during events like solar eclipses, moon cycles, and even planetary alignments. A black hole merger, especially one within a few thousand light-years, would be orders of magnitude more intense. We might not recognize the effect, but feel it nonetheless. Meditation, dreams, and the gravity within. Here's a different angle. Advanced meditators report losing the sense of time, space, and even self-entering states where everything is one, and consciousness just is. Could these states be mini black holes of the mind? Regions of ultra-concentration, where internal gravity bends thought inward. Some neuroscientists have compared deep meditation to localized gravitational effects on brainwave frequencies. Now imagine if an external gravity wave, from a black hole merger, coincided with such a meditative state. Could it trigger a state of enhanced awareness? A moment of fusion between the inner and outer universe. It's speculation, but it resonates with mystical traditions across time. The brain as a quantum receiver, evidence. Recent studies in quantum biology suggest that photosynthesis, avian navigation, and even human smell involve quantum effects, so the idea that brains might harness quantum coherence isn't fringe anymore. If that's true, then sudden gravity spikes, like those from a black hole collision, could jolt these delicate states. Think of it like tapping a crystal glass. A sound wave you can't hear might still shake the structure. Consciousness might shimmer, wobble, or pulse in response, leaving us with strange dreams, inexplicable insights, or feelings of profound awe. The singularity as a mirror of the mind. Let's get metaphysical. A singularity is the place where space and time end, where equations break, and reality as we know it becomes undefined. Consciousness, too, is a singularity. We can't observe it directly. We can't model it precisely. We don't know where it begins or ends. Could it be that the singularity within us, the observer, the self, resonates with the singularity out there? Perhaps, when black holes collide, some part of our deep unconscious recognizes the event, not with language, not with thought, but with silence. The kind of silence that feels cosmic, heavy, unspoken, timeless, the merging silence. And so, as we drift beyond the last gravitational whisper of two merging black holes, we're left with a strange kind of silence. Not the absence of sound, but the stillness that follows understanding. A moment where the mind, stretched like space itself, tries to comprehend the impossible. Two black holes, once titans of cosmic isolation, becoming one. A singularity embracing another singularity. A union where time fractures, light folds, and the laws of physics bow in reverence. It's not just about gravity or mass or equations. It's about what happens when reality reaches its edge and decides to continue anyway. You've just wandered into that liminal space, the edge of known science, an unknowable wonder. If this journey through the deepest folds of spacetime stirred something in you, a question, a dream, a quiet awe, then you're exactly where you need to be. This is Mind Scramble, where reality is only the beginning. Subscribe to stay on this path with us. Turn on the notification bell. The next unraveling is already approaching. Drop a thought in the comments. If you could witness two black holes merge, would you watch or turn away? Until next time, sleep deeply, think infinitely,